Good afternoon. Thank you for everybody joining us. Thank you for this opportunity that you guys have given us to, design a solar array. This is a very, very cool opportunity. I just wanted to start that off by saying thank you for that. Our team consisted of 8 students and 2 professors from a pretty wide variety of fields of study in order to broaden everything when presenting everything with the project and presented with issues or questions in the project. The co-captains were myself and Christoph Nischwitz, who you saw earlier. And the 2 professors were Dr. Randall Ellingson and Dr. Colin Gilstrap. Dr. Ellingson is a professor of physics and Dr. Gilstrap is a professor of finance here at the University of Toledo. The other students were Philip Oettinger and Ernest Wolke, who led the distribution analysis. We had Wyatt Mowry, Ernest Wolke again, and myself lead the array designs. Andrea Van Kam and Sanat Vaj led the financial analysis with Dr. Gilstrap, and Brock Lohr led the development plan and all related fields with that for the project. The basic summary of our solar plus storage solution was we started with a couple of building tops, the largest building top arrays to cover the likely largest buildings that would swallow up the most power on the campus. And then we went to the floating array and the proposed ground solution. We were able to cover around 72% of the energy profiled with only 4 arrays and a combination with a battery installation. The panel that we decided to go with was the Q-Peak Duo, as you can see on the screen. It is rated for 390 watts of electricity with individual cells producing 2.7 watts. The efficiency of the panel is rated around 19.4% from the ray of the sun to the energy produced, which is near the top of the industry standard. We chose to use 2 different inverters. First, microinverter, which you can see here is the IQ7 Plus. The microinverter has the ability to individually control panel energy production, and that has a 97% efficiency. And then the string inverter, while not having that individual panel control, and it would go by strings, did offer a cheaper overall production or overall installation and everything, and that actually had an increased efficiency of 97.5%. You may have noticed that the actual manufacturer warranty for all of these products is 25 years, which was honestly just very convenient. Then the solar solution we used is the Tesla Megapack lithium ion battery. It is a 2.7 megawatt hour storage capacity, which is about 30% of the daily load, with a 4-hour cycle up to, you can read there, and then a 90% round trip system efficiency. This is the most energy dense battery solution on the market, which is why we decided to go with it.
Our first rooftop array was designed for classroom building 1 and consists of 827 panels, making up 46% of the energy offset for that building, producing roughly 452,000 kilowatt hours. It has the highest annual solar access of all the rooftop arrays at 98.7%. It is important to note that for all the arrays being displayed today, the tilt and panel orientation was optimized to allow for the most solar access. All panels will be installed facing true south and will be in landscape position. Our second rooftop array was designed for engineering building 2 and consists of 558 panels, making up 17% of the energy offset of this building. Producing roughly 320,000 kilowatt hours, the annual solar access is 98.2%. Please note the location of our rooftop arrays were selected for their lower shading interference and that all panels were positioned to avoid shading from the building and self-shading. Moving on to our floating photovoltaic array. This is located on the pond just east of the football stadium and north of the softball complex, a perfect position to be seen by people traveling to and from sporting events. This array is designed to resemble the UCF Sword and Shield logo and can be a source of school pride. Consisting of 3,023 panels, this array produces roughly 1.7 million kilowatt hours and has an annual solar access of 97.2%. And last but not least, we have our ground mount array, which is located in the midst of multiple hiking paths southeast of main campus and covers around 6.17 acres. This array consists of 13,552 panels, producing roughly 8.5 million kilowatt hours with an annual solar access of 99.5%, the highest of all 4 of our arrays. It is important to note that in the process of designing and implementing this particular array, the land must be cleared of trees present. This is why we would highly suggest introducing the idea of agrivoltaics to this array. We have composed a list of native and endangered plants, Florida plants that we think can thrive between the spacing of the panels. This would add a unique and beneficial component to both the array itself and UCF campus.
Proposed systems were all consciously designed with the constraints of the distribution system in mind. Due to Florida's lack of net metering, we used campus substation load data to determine a daytime minimum load of around 2,300 kilowatts, which our total array capacity could not exceed. This excludes, of course, the ground mount system, which has a unique status and ability to sell power to the utility. We connected our building arrays on site behind the meter, our floating system to the nearest transformer, which required a power rating upsize, and our ground mount system directly to the nearest substation. During the initial analysis of simulations with our added PV, we determined that the floating array was contributing to a maximum overload increase of 10% over pre-PV levels. However, we noted that both of our building arrays in combination only caused a maximum increase of around 5%, and there were no voltage exceptions created, which was expected. I say this was expected because during the selection of our inverters, we ensured that the voltage output would be within the per unit voltage limits for the voltage bases of the array's connection points. In addition, using a gentle volt-var inverter control curve, we were able to entirely offset the overloading impact of each of our building arrays. Unfortunately, inverter control methods were unable to significantly quell the impact of our floating system. And to address this remaining grid impact risks, we have two proposed solutions. The first and more preferable option, the inclusion of our battery storage system into the final project development, or if need be, as a last resort, a downsizing of the floating array.
The financial analysis focused on 5 main inputs to hit the targeted IRR of 8% and NPV of 0 or greater, like it was outlined in the rules. We came to the arrival of total cost per watt of $1.52, estimated P50 solar production kilowatt hour per kilowatt of 1,618, PPA price of 8.6 cents, PPA escalator of 2.5%, and project sale price of 13.6 million. I just want to say again that we focused heavily on the IRR and NPV, so we had an IRR of 8%, which matched the hurdle rate, and an NPV of $2,026. We also found the annual lease payment of $257,000, or a monthly lease payment of $21,000. We estimated the annual customer savings to be the average annual customer savings would almost be $248,000, and then in year 20, the savings will be $297,000.
So for our development plan, we have 2 primary groups that we want to appease to, maintain communication with. The first group is what we refer to as the stakeholders. These are the county university representatives that make a significant role in decision-making processes of the university. So we're planning on appointing 1 representative member of our development plan team to act as the primary liaison between the stakeholders and our team. So this liaison will hold the primary responsibility of engaging and maintaining communication with these stakeholders. And with constant communication, we plan to continuously provide progress updates regarding project development and takeoff. And with these updates, we will record, address, and forward any stakeholders' questions and concerns with our team. Second group is what we'll refer to as the community. So this includes university students, faculty, and staff. And like with the stakeholders, we hope to maintain this communication with the community by signs of or means of signage on campus and their email distributions to discuss the project importance, as well as the impact of the project that it will have on UCF campus. Additionally, we'll plan on holding monthly town hall meetings on campus to discuss with the community about our progress on the project, and be open to record and discuss any questions and concerns with the community. So generally, throughout the design and construction processes of this project, applicable legal codes, which include Florida Building Code, Mechanical Code, Fire Protection Code, and the National Electric Code, must be adhered to. So the importance of this compliance and adherence is pretty simple. We just want to administer safety to all those involved in the construction and those impacted by the project completion. We also want to avoid potential litigation by not adhering to these standards, and we want to provide guidance to those who are contracted to complete the construction and installation work. Furthermore, with the construction stage of this project, the biggest challenges we'll face include ground mount array or the tree clearing array. So as Wyatt mentioned earlier, trees will have to be cleared, but also we have to consider construction challenges with regard to soil composition. But looking at the figure pulled from the U.S. Department of Agriculture's web soil survey, as you see on the slide, there appears to be 2 different soil areas where our ground mount array will sit. Near the center of this figure, 2 areas that are considered. First one's area 34, which is inside the bubbled regions, and area 44 outside the bubble. And generally, we conclude from the data we collected that these 2 areas are primarily comprised of fine sands with approximately 0 to 5% slopes. So the construction implementation, our team would recommend for the array to follow the contour of the land. So this method is very cost effective since additional contractors do not have to be hired for excavation and fill for providing a more smooth surface on the land. And with regard to supporting our array structurally, we recommend driving helical piles on the ground. And we recommend this because sandy soils are typically weaker than other soil compositions. And more specifically for the pile embedment depth, recommend following ASCE 7 standards and calculations. And we recommend these to be used while factoring in different load combinations to consider the structural integrity of these arrays. Let's put together a preliminary construction timeline for the entire duration of the project. So as you can see, the project has been estimated to be completed in about 12 months, while spending 8 of these months in the development stage. So more specifically, this stage includes 6 different phases, which consist of site control, which is general and preliminary nature, followed by permit preparation, application, power offtake, project financing, interconnection, and engineering. So once all these phases are completed, the construction stage can commence. So this stage is estimated to be completed about 4 months with 3 different phases, including completion and distribution of all construction documents, construction material procurement, and the actual construction of our arrays.
So the largest benefits of our system are going to be found in the financial savings and our major focus on safety. Our systems were designed with safety being the first and foremost thought. When we actually were first presented with everything, our very first question was, what are the national codes and what are the local codes that will be required to be adhered to in order to make this the safest learning opportunity for any students who are going to have the ability to study this stuff while they are at UCF. As somebody had mentioned before, this is an educational institution. We believe students who attend the university should be able to study in a very, very safe environment, very controlled environment. We also took great pride in the creative design of our floating pond array. That took a lot of work by Wyatt Mowry, one of our members. It's located next to the bounce house, as he said, and it is visible from the North Orion Boulevard that passes right next to the pond, between the pond and the bounce house. As well as our plan for agrivoltaics being used in the tree clearing array. We found a list of, we purposefully looked through lists of plants that were endangered and native to Florida that would most likely thrive with limited water and weird shading interference. And those are the plants that we are prepared to find, and that would broaden the scope of students that are able to study on these arrays. That can allow environmental engineers to become more familiar with solar arrays and the opportunity to plant plants between each panel system. And then for the financial analysis, the very favorable project with an NPV of $2,026 and an IRR of 8%, an average customer savings near $248,000 per year over 20 years is a very, very favorable number for this 7.05 megawatt DC capacity array that we didn't mention before. It produces around 11 gigawatt hours of power annually. And it'll allow the university to make around $11.1 million in profit. Just like to take this opportunity again to thank you so much for this opportunity. Thank you to UCF for allowing us to investigate your campus, I suppose, to design these arrays. And then thank you to the NREL for giving us this opportunity to compete with other institutions for this amazing opportunity. Thank you.